Welcome to UAB Data Science Club number 31. Today we're going to talk about the kind of underpinnings of deep learning with something called convolutions. So, and the convolutions isn't the only thing that happens in deep learning, but it's a really important thing, especially for complex data like images. So the website we're going to go to is kaggle.com/learn/deep-learning. And we're just going to take a quick look at just the first lesson in there, and we'll kind of go from there.
So it has been some time since I took signals and systems while I was doing computer engineering in my bachelor's. So I remember a bit of convolution. So it's like a filter that you pass over an image, right?
Yeah. I mean, if you've watched Stranger Things, when they're playing with that like Ouija board, and they have like the little magnifying glass that they move over the board, that's convolution.
Okay.
Is that you're using some filter. In the case of Stranger Things, they're using that little magnifying glass, and they're passing it over some piece of information, which is the board, in order to get some new information out of it. And so that's the basic gist of convolution. So
Okay, all right, that gives a good explanation.
Yeah, and so one of the reasons why convolution is important to understand for machine learning and deep learning in particular is that when you get into these really large, complicated deep learning architectures, one of the things that happens, so we did some feature engineering last year. So convolution layers in a neural network basically allow you to automatically optimize and figure out what filters would be appropriate for a data through the optimization process, rather than requiring you knowing ahead of time what those filters should be. So if there's salt and pepper noise that's there, maybe the network automatically learns that it needs to run a median filter to remove that noise before then you are making your decisions. Or if the edges are important so that you can tell what an object is, what the outline of an object is, then it would learn a variety of edge filters to extract those hierarchical components.
So as a programmer, you have to focus on what you want out of that convolution. Yeah.
So traditional neural network building, when I took pattern recognition in 2009, something like that, you would have to build your convolutional filters before you built your neural network. And then in today's world, convolutional filters are built into the neural network, and so you no longer are tuning them by hand. And so that's why it's important to know what they are and what they're doing, is because it's in there, but it's much less complicated from a programming standpoint, because I don't have to know ahead of time what an edge filter looks like. The neural network is going to build those edge filters for me.
That sounds perfect to me.
So yeah. I don't think this notebook is too involved, but that's okay because we don't want to overload, especially when we get to really complicated topics like convolution. So you can see in this diagram, they have this thing called a kernel. So that would be essentially the filter that we're wanting to run over things, or like that spyglass or that magnifying glass in Stranger Things. And then we run that over our input data, which is another matrix. And so you can see it covers these 9 pixels, we'll say. And then from knowing that neighboring information as well as the information in that center pixel, then it gives me a new result in my output data.
Okay.
And so then by combining these filters, we get more complicated hierarchical feature sets. All right, so let's see. First things first, we've got to import the learning tools so it can check our answers. And then, all right, so we didn't watch the video. There's a video attached to this exercise. Go ahead and watch that before you hop in this. If you like, we're just hopping into the code to just start playing around with it and seeing what we can do. So it doesn't look like we're changing this filter, but this is really nice and indicative of what a convolutional filter does. So this one detects horizontal lines. So if I'm running this filter over at a location in the image, if I multiply this matrix by that location in the image, if there's a horizontal line there, then it will give me a large value. But if there's a vertical line there, it will return 0.
What about the ones that are not horizontal or vertical? I mean, if there is some...
Then it will give me the horizontal component of that.
Oh, so it might be lighter than a completely horizontal line.
Yeah, so if we run this, then we can see that while certainly like on the left side of the dog here and on the right side,
we have some...
there are vertical lines there,
Yeah.
but I'm not seeing them in my output over here. It's almost like they've disappeared.
Yeah.
Whereas right on top of his head, you see a really strong response.
Yeah, and so like you were mentioning that if we have something at a diagonal, that diagonal line that has component from both vertical or x or y axis, then depending upon how slanted that line is, it can get more deeper definition or much lighter definition.
Yeah, and so now this next part, we're really trying to understand the convolution. So it wants us to build the vertical line detector. And so if you can imagine, this is the horizontal line detector that I put in there right now. And so you've got ones and then -1, so that if it runs up against something horizontal, then if I multiply that, it will give me a strong number in response. So basically, I want to change this so that instead of ones on top and -1s on bottom, it should be ones on one side and -1s on the other side. And this isn't the only vertical and horizontal line detectors. This is just one example of one, because certainly you could put ones and zeros and you would get a similar feature set out. So that's another reason why it's nice that in convolutional neural networks that's taken care of in the background, is because there's so many different options that you could pick.
Yeah.
All right. So now this is what we were talking about. So now we see from the vertical line detector.
Yeah, so now the trees and the head of the dog, all those things are more prominent.
Yeah.
Even the shape of his back is more prominent because that's more vertical than horizontal.
Yeah. But then you see like the bottom of his paws down here.
And plus that horizon behind his ears, that's very light because that's almost horizontal.
Yep, exactly. All right, so now it's saying, we've seen 2x2 convolutions, but there certainly could be 3x3 and 4x4.
Now that gets...
and they don't have to be square.
Yeah, sorry. Before we go to exercise 2, that gets me thinking. What happens if I do a complete negative one on all?
Oh, just -1s on everything?
Yes.
Yeah.
Oh, that's a complete.
So you've just inverted the image,
Yeah.
right? You inverted the colors of the image. And then the other thing that you could do, which is also really interesting, is to do diagonal filters like this.
That takes away a lot from the features that you could see inside.
Yeah. Well, and then like sometimes I think if you're going to do a diagonal filter, you really want it to be more like that. Yeah, there we go.
This gives us a very decent edge for the entire image.
Yeah, and this what I forgot is that when you're doing the diagonal filters, you want to zero out the diagonal that you're not interested in.
Okay. Very interesting.
Yeah.
Alright, so this is how when we are running, just going into the future, maybe the videos that we'll be doing next week and over the coming few weeks, this is how we'll see that, okay, we can see that there is a shape of a dog over here, and then that's how we can start recognizing that if we see this shape, then there must be a dog inside that image.
Yeah.
Alright.
All right. So let's see. I think this is just a question, and then I think we're done for the day. So the convolutions we've seen are 2x2, but they could be larger, 3x3, 4x4. They could be non-square. Compare the number of visual patterns that can be captured by small convolutions. Which of the following is true? There are more visual patterns that can be captured by large convolutions. Fewer visual patterns can be captured by large convolutions. The number of visual patterns that can be captured by large convolutions is the same, blah, blah, blah. Okay, so I would say that you can capture a larger you could capture more visual patterns with larger convolutions. It just gets more complex.
I mean, so the basic idea is that if we have a larger filter, then it would include more pixels from the side of the main point that we're looking at. So wouldn't it just more flatten or smoothen out?
Well, so like for instance, in a 2x2, I can do up, down, left, right. I can even do diagonally, like what we saw, but I couldn't do a curve.
Oh, okay, yeah, that's true.
But a larger convolutional kernel could theoretically do a curve.
Oh, okay.
So that's where I'm saying it could do more. Let's see what they're saying. There are more possible convolutions that can be created with large sizes. Yeah.
Yeah, so there are also more patterns that can be captured.
Yeah, and then certainly the other thing is once you go to like a 3x3, then you can suddenly do like a median filter or an averaging filter over a larger space to do some denoising and things like that, and not just direct feature extraction. So yeah, well that's good. Yeah, I think it's nice to take a minute to just look at convolution. That may seem like a little bit of a side direction, but when we get into using deep learning to do image processing, then it's going to be really helpful to have taken a minute to think about convolutions.
Yeah, it's something that is a little difficult to visualize, or at least that was the experience with most of the people that I've studied with for that course. It's a little difficult to visualize, but it's all about clicking. I mean, if it clicks that how that convolution, that filter layer is going, it might become easier. So yeah, it would be good, like William mentioned, just to think about it, go through the video that's associated with this exercise as well. They have useful information as well. So
yeah, and don't stress out about the difference between machine learning and deep learning at this point. We'll talk a little bit more about that as things come up later. Just suffice it to say that we're using convolutions right now as a building block to getting to convolutional neural networks, which is a type of deep learning architecture. Oh, excuse me. All right. Well, thanks, guys, and yeah, we're excited to keep going this semester and get more out of all this data science stuff.
Talk to you guys next week.
Yeah.